In the previous lesson, we talked about logarithmic functions. So today we're going to transform logarithmic functions, and hopefully you're an expert with transformations by now, because in grade 10 you transform quadratic functions after you learned about quadratic functions. In grade 11 you transform the root function, the absolute value function, the square root function, a linear function, you transformed exponential functions, you transformed trigonometric functions. You've been transforming for quite a while by now, so hopefully you're an expert. So transforming logarithmic functions is no different than transforming any other function. You make sure you establish what the parameters are, and once you do that, you apply the transformations, find out the new points, and then you're done. So we're fresh in your mind because we did recently transform trigonometric functions. So you have the four parameters. C tells us the vertical translation. D tells us the horizontal translation. A tells us the vertical stretch factor. And it also tells us if there is a reflection with respect to the x-axis. K tells us the horizontal stretch factor. And it also tells us whether there's reflection with respect to the y-axis. Okay, so establish what the transformations are by looking at what the parameters are. And then, once you establish what the transformations are, you should be able to generate the mapping rule. So you know how the x values are affected and how the y values are affected. And you can determine where the new location of the transform points are. And once you have the new points, you plot them and you connect the dots. So, the one thing that is a little different about transforming logarithmic functions is that it really depends on the base of the logarithmic function. And that is analogous to what you learned last year when you transformed exponential functions. So for example, last year you should have transformed y equals 2 to the x. And you should have also transformed y equals 3 to the x. Okay, the original points of 2 to the x is obviously different than the original points of 3 to the x. Okay, you can also say I'm transforming y equals half to the power of x. Okay, the points are very much, they're different, of course. They're different functions. So we said last year for exponential functions, your x values will range from -2 to 2, and then you solve for the corresponding y values. Okay, so that idea is very similar to logarithmic functions because the original points which you're going to work with for a logarithmic function really depends on what the base is. If the base is 2, you'll have a set of points. If it's a base of 3, you'll have another set of points. Okay, so in the next page, we're going to look at logarithms with different bases and establish what the key points are, which we're going to work with. Okay, so this table I have here is from for y equals log base 2 of x. Now, I just want to take a look at this table and see how the values are generated. Because if you're not very good with logarithms yet, then a strategy you can use to generate this table very quickly is think of the inverse. Because the inverse of a logarithmic function is an exponential function. So hopefully you can envision the inverse of this logarithmic function. And you should get y equals 2 to the x. Okay, so if you think of y equals 2 to the x, you're really good at powers. So you should be able to come up with the table for y equals 2 to the x. So let's do 0, 1, 2, 3. And then 2 to the 0 is 1. 2, 4, 8. So that table corresponds to this table, right? They make perfect sense. X becomes y, y becomes x. So the strategy we're going to use is for the y values for the logarithmic function, we're just going to set them to be 0, 1, 2, 3, and then use powers to figure out what the x values are. So let's try that here. So for example, y equals log base 5 of x, no problem. 0, 1, 2, 3. So the x values would be, what's 5 to the 0? 1. 5 to the 1, 5 squared, 5 cubed. Okay, so these are, if I'm asked to transform log base 5 of x, I'm going to use these points. Log base 3 of x, 0, 1, 2, 3. So 3 to the 0, 3 to the 1, 3 squared, 3 cubed. Y equals log x, common logarithm, so base of 10. 0, 1, 2, 3, 1, 10, 100, 1000. Y equals log base 4 of x. 0, 1, 2, 3, 1, 4, 16, 64. Okay, so it really helps to always keep in mind that a logarithmic function is the inverse of an exponential function. So just in case you can't answer the question, always try to revert to something you do remember, or something that you're very good at. Okay, so now let's sketch some, or let's transform some functions and sketch them. So in addition, for this question, they ask us to find the x and y intercepts. So let's start with x-intercept, which means I have to let y equal 0. This is just a very basic logarithmic equation we're going to solve. Later on in this unit, we're going to solve some more complicated logarithmic equations. But this one we can manage. There's nothing too intense about this. So, logarithmic form, whoops, exponential form. So x is 34. So y-intercept, let x equal 0. Oops. Now, this is undefined. Log base 2 of negative 2 is undefined, because you cannot have an argument which is less than 0, or even 0. It has to be greater than 0. So since log base 2 of negative 2 minus 5 is undefined, then we can say no y-intercept. No y-intercept. Okay, so let's generate the mapping rule. This one's pretty straightforward, because we're going to shift 2 units to the right and 5 units down. So take the previous x value, subtract by 2. Oh, whoops, add by 2, because you're going 2 to the right. And then you go 5 units down, so take the y values and subtract them by 5. Alright, so we need the original points. So I'm transforming log base 2 of x. So 0, 1, 2, 3, 1, 2, 4, 8. So add everything by 2. 2 plus 2, 4, 6, 10. Subtract by 5. Okay, let's plot these points and we're almost done. So 3, negative 5. 4, negative 6. 6, negative 7. And 10, negative 8. So for every logarithmic function, it'd be really helpful if we sketched in the asymptote, the vertical asymptote. Just like for an exponential function, you always sketch in the horizontal asymptote to increase the accuracy of your graph. So for a logarithmic function, we're going to sketch in our vertical asymptote. So the question is, where is our vertical asymptote? Well, originally, it was on the y-axis, okay? But now, after we apply these transformation, it will no longer be on the y-axis. So the horizontal translation actually dictates where your vertical asymptote is going to be, which makes sense because if my vertical asymptote used to be on the y-axis, the horizontal translation will dictate where my vertical asymptote is going to be. So since I shifted 2 units to the right, the vertical asymptote should be now located at x equals 2. So with exponential functions, your horizontal asymptote is dictated by your vertical translation. And like I said, they're inverses of each other. So this idea is very similar to what you learned last year. When the horizontal asymptote was dictated by the vertical translation, it's exactly the same. So now we don't have a horizontal asymptote anymore, we have a vertical asymptote. And that positioning of the vertical asymptote is controlled by your horizontal translation. All right, let's keep transforming. Yeah, let's just go for it. X-intercept, y-intercept. Let y equal 0. Divide both sides by 5. Exponential form. Okay, y-intercept. Just show all my work, just in case you find it hard to follow, because you're still relatively new to logarithms. Okay, so now I want to find the new points. Whoops, I forgot the mapping rule. So, what are the transformations here? Vertical stretch by a factor of 5, horizontal translation 3 to the left. So, I take my x value and subtract by 3 because I'm going 3 units to the left. And then I'm going to take my y values and multiply by 5 because I'm horizontally stretching by a factor of 5. Sorry, I'm vertically stretching by a factor of 5. Alright, 0, 1, 2, 3. That's a base of 3, so 1, 3, 9, 27. I'm probably not going to plot this last point, but I'll write it anyways. With logarithmic functions, based on how quickly the x values grow, it's unlikely that you'll get 4 points. Like 2 or 3 points is actually very good already. Okay, so if I subtract by 3, so -2, 0, 6, 24, and then multiply by 5. Okay, so the first thing I'm going to do is actually I'm going to sketch in this vertical asymptote. So I went 3 to the left, so now it's going to be at x equals -3. And let's plot those points. Oh, what do you know? X-intercept, y-intercepts, I can see them from the table. So x-intercept of -2, y-intercept of 5. So I'm happy. The math is matching up so far. 6, 10, 6, 10. Whoa, this is very faint. So somewhere about here. All right, let's connect the dots here. Beautiful, nice. All right, one more to go here. Y equals log of -2x plus 4. So x-intercept, why not? So we'll let y equals 0. Okay, and then exponential form, and this one's going to be some ugly number. -5 times 10 to -5. I'm definitely not going to plot that. I can already see that there's no y-intercept because I see no horizontal translation, which means my vertical asymptote is on the y-axis. And if it's on the y-axis, there's definitely no y-intercept. I'll do the math nonetheless, but I already have an expectation of what I'm going to get. Yep, log 0. What do you know? No y-intercept. Alright, let's do the mapping rule. So, there's reflection with respect to the y-axis and a horizontal compression by a factor of 2. So, that should be the first part of your mapping rule. You take x and multiply by -½ and then you shift it 4 up. So you take the y values and add by 4. Okay, I'm doing a base of 10 here. Ooh, so these numbers are going to grow pretty quickly. So we'll multiply by -½ add by 4. And then sketch in the vertical asymptote. Plot what I can, -½ 4, oops, wrong way, -½ 4, -5, 5. Okay, all I can get those 2 points, no problem. That point wasn't very good. I didn't really pass through nicely, but it'll do for now. Okay, so for all these, define x and y-intercept, you're really just working with your knowledge of logarithms, but the transformation part, I know the graph of a logarithmic function is new, but the transformation part, finding the new points, the algebra involved there is hopefully very reminiscent of what you've done before. I will recommend you to just really think of exponential functions when you try to find the original points or the points you're transforming on your logarithmic function. Okay, one more question to go. So, state the transformations applied to f of x equals 4 to the x to obtain g of x equals -2 times 3 to the power of x. So this question is a nice twist on what you did last year. Now, because you learned about logarithms this year, you can do this question. If I strictly force you to work with exponential functions from last year, you can't do this because you have a base of 4 here and a base of 3 here. Now, 4 and 3, they're not friends. And what I mean by friends is that you don't know, well, from last year's knowledge at least, you don't know how to express 3 as a power with a base of 4. You don't know how to express 3 as a power with a base of 4, right? If, for example, if this was like 16, if instead of 3 it was 16, no problem. Write as 4 squared and then you're done. But 3 and 4, you don't know them as a friendly relationship. So what I'm going to try to convince you is, or what I'm going to try to show you how to express 3 as a power with a base of 4. So 3 equals 4 to the power of something, okay? Because once I have the same base, I can state the transformations. So 3 is equal to 4 to the power of log base 4 of 3. So take your time and digest that. Okay, I promise you that this is true. This statement is definitely true. And you just have to explain to yourself why it is true. Okay, so take your time, look at it. You can pause the video. So I'll try 2 different ways of explaining it. Now there's one really short way of explaining this, and that is that powers and logarithms are inverses of each other. So with that simple fact, as long as the base of the power and the base of the logarithm are the same, then this relationship is true. In fact, you can argue if this is A and this is B, this is always true as long as, of course, A is greater than 0 and B is greater than 0 and not 1. So as long as those restrictions are fulfilled, this is true. This is an identity. Okay, this is based on the fact that powers and logarithms are inverse of each other. Now, if you don't see that relationship, if you find that very hard, then you know what? Just go back to your understanding of what a logarithm is. Okay, so let's play with these numbers. Okay, log base 4 of 3. This is saying 4 to the power of some number is equal to 3. Okay, that's what this is. Well, I'm taking 4 to the power of that some number now. Of course, it's going to be 3. So I'll try to make it even friendlier. I'll use some nice friendly numbers. So let's say this is 4 here, and this is 2 here. 2 raised to the power of what will give me 4? And the answer is, of course, 2. And now I take that base of 2 and raise to the power of 2. Of course I'm getting the 4, right? This is the exponent I needed to get 4 with the base of 2. So this makes perfect sense that they are indeed equal. Okay? You know what? Maybe I'll change the number because I don't want this 2 here to be the same. But like I don't want the exponent to be 2 as well. So let's do 8 instead. Okay. Log base 2 of 8. That is asking me what is the exponent with a base of 2 to get 8. Okay, what is the exponent of the power if the base is 2 and I want the result to be 8? Of course the answer is 3. And then I take the 2 and raise the power of the 3 to get the 8. Okay. Anyways, you can take your time, think about the relationship, but it's definitely true. So why did I show you this? Because now I can re-express g of x as a power with a base of 4. Power to power, so multiply exponents. Okay, so what are the transformations? So vertical stretch by a factor of 2. Reflection with respect to x-axis. And horizontal stretch by a factor of the reciprocal, which is 1 over log base 4 of 3. Later on, you're going to learn there's a new way of, or a simpler way of writing this, but for now, we can definitely live with that. Okay, so hopefully that wasn't too bad, and the good news is this is the last time we're going to talk about transformations for this course.